what's the value of it? And it takes on values along the real line. What's the value of it? Marco.
So
You can't. If I had a random variable x, it's a scalar, and it takes on all values along the real line.
I can just say that it's going to be between the range, but I cannot say that.
You cannot say.
Yes.
But if I slaved x to time, that is x equal to t is a deterministic variable, it's no longer random. You can't predict it. I mean, you can predict it now, what it's going to be. Okay? So that's a random variable. So, Marco, I always want to say Luca. And you don't mind if I call you Luca. Okay, so,
No,
given these guys, which one's a random variable, which one's not?
Y is a random y.
Well, in this case, I'm going to define x as my random variable.
But if y is 1, y is 0.
But w is a fixed variable, so it's not random. But I'm going to put it in there anyway to remind you that it controls the output somehow. And x, in the context of our photographs, is a photograph of a motorcycle a random variable, the intensity values? Look, man?
No.
What do you mean, no?
We,
You're a perfect photographer? You never get errors?
yeah, in that case.
Okay, you always get errors. Okay? Each pixel has some kind of intensity value that should be there, but it's not.
Yes.
It's plus or minus something. So indeed, each element of your photograph and the intensity is a random variable. Now, judging it to be if this has a relationship, if there's a relationship between x and y in some way, that means y, because x is a random variable, that's going to be a random variable. Okay? But w isn't. It's just a deterministic set of numbers. So here's what happens with this particular binary conditional probability function, CEF. If y is equal to 1, it's a red motorcycle, then I claim it's equal to this probability distribution. If y is not equal to 1, because it's a binary function, the only other outcome is it's not. So if this is the probability if it is, what's the probability of it being not that outcome?
Okay, it's 1 minus.
Okay. And we know this to be that, and I've already shown you what 1 minus g looks like. It's just the flip version of that. What's the matter, Abdullah?
No, just.
You do it in your head? Come on, let's do it again. 1 minus that kills this and bumps up that. Got it?
Yeah, it's clear.
What?
It's a clear. That's if you subtract that from 1. Okay.
Okay, now we get to PDF. We remind ourselves something we learned in either high school or early college. Not PDF, but this is conditional probability function. This is a definition of a conditional probability function. Abdullah's going to tell us what's what.
The definition of what?
Which one is which? Relate these guys to, there's 3 probability functions in there.
Okay.
Okay, this guy's starting to laugh. Okay.
No, I have no idea.
What's your name?
Li.
Yi?
Yeah.
Yi?
Li.
Oh, Li.
Yes.
Okay, Li. Relate which one of these names to the 3 terms on top? What's this?
John.
Drawing. I think the one on the left of the equation.
This one?
No, that one.
This one?
No. Yeah, this one.
Oh, did I put that in the right order?
Yeah.
Yeah, that's what I was thinking.
Okay, so this guy is that. And funny about that, they call it a marginal probability. And Marco's going to tell us why they call it a marginal probability.
Because they integrate out the other random variable.
What does that mean?
The other random variable is integrated out.
Can you put the equation up there?
About the
Tell us what you mean precisely.
for all the possible variables.
All the possible variables for what?
So you get, no, sorry, these plates. So this is the marginalized one.
And why do they use the word margin?
because you marginalize out, like, because you integrate out, so it's a margin one.
There's
So.
got to be a better intuitive connection between marginalize and that. They should have called it the integration variable or
Yes.
something.
I don't know, because you margin, so it's a margin of the.
Margin
So,
It's like if we shouldn't get
part
signed.
of it.
Okay. Well, I'll think about it.
Because in Italian, it's Latin. In Latin makes sense, but in English I don't know how to say.
You know, I took 2 years of Latin.
Because margin,
I took 2 years of
I
Latin.
studied for 7 years.
Hey,
At the high school in Italy, you study more Latin and then the mathematics.
you remember it?
Yes.
I don't remember words. Oh, I remember words.
But I appreciate that in the book you put the numbers in Latin numbers.
They said it would be good for science if you go into science. And as a freshman sophomore, I thought, oh, okay, I'll go into science. I better. Did do me a bit of good. Okay.
Yeah.
Okay, so let's quickly look at the intuitive proof of this relationship. P of x, y is the intersection. When does x and y intersect one another, or when do they occur simultaneously? Well, that's going to be that little area there divided by the big area, right? Little area, the intersection area, x and y, divided by the big area, just by using your intuitive understanding of probability. So this should be equal to that. Let's see if it does do that. Okay, this intuitive understanding of P of x is, well, it's the area of the big blue here divided by the big A, the x of the big A. And tell me, Abdullah, how did we get this? Why is it intuitively obvious the conditional probability is the ratio of this little intersection area divided by A of x?
The conditional probability of y. Okay, so you want to see what's the probability of y provided a given x.
X is already, x has occurred.
Okay, it's the intersection, so you take all y, you divide by it.
Okay, here's the intersection.
Yeah.
But why divide by A of x?
So you only left out with y.
Well, yeah, our universe used to be the big purple area. But then our universe got shrunk when we said, no, x occurred. And if x occurred, that's our universe now. So which part of x occurred do we have also at the same time A of y, so that little intersection here. So that's going to be our ratio of what could occur versus what has already happened. Okay, so that's just that. And then these things cancel out.
Can I? Yes. I think it should not be the P y x because their reading is a y given the value of w and x. But should not be the other way around. Should not be written like wx given y. It should not be which.
What are we? Which?
No, up, the black one.
This?
Should not be wx given y.
No, this is given x and w. What's y?
But then you brought the other way around. You give value to y to define w and x.
Say again. What?
But then on the right side,
Yeah.
you give value to y to define what is the value of wx. So it should be the switch.
Well, here's our input. It's occurred. I mean, it's a random variable. And if you have this input, this will describe what the predicted class will be.
But then f will
But
not make sense.
you define
Yeah.
w and x over the value of y. You say if y is equal 1, then is going to be g over x. Oh no, wait.
Think of this as heads and tails. Well, let's think about this. Okay,
Okay.
but not now. Only again. Okay. A more compact way of expressing that is this.
Okay.
Okay.
So,
So that is. Did I make a mistake? No, I didn't.
No.
So okay. So more compact. So let's see if that's true. If y is equal to 1, this guy is 1 minus 1 is 0, so it's going to be a 1, and you're left with that. If y is equal, there's only two outcomes, right? 1 or 0. So if y is equal to 0, this is 1. We're left with, no, y is equal to 0. This is alive, and this is 1. And that replicates that. Okay. So that's a compact way of expressing that. And and I already gave you this example. If this is the probability of something occurring, something not occurring is just take the one and subtract. Okay. So what we'd like to do is find a W that maximizes this probability. That is really, somehow we can control our prediction by fiddling with the W's. And if we control our prediction, we'd like to, make a perfect agreement, if we can, between the predicted value of y and the observed value of y, the classic ones. So since we're trying to maximize this guy, this is called a maximum likelihood function, or problem. But it's a lot easier to do things in a minimization sense. We don't like to go to the top of a mountain. We like to go down to the bottom of the Po Valley because it's easier for mathematically. So how would we turn this into a minimization problem, Marco?
Integrate with respect. Take the derivative with respect to y equals.
We do something fancy like that. But we're not fancy in this class.
So the stochastic descendant.
What's a real simple, quick and dirty way to do this? Look, man. If something's a mountain, how do you turn it into a valley? What?
Give a minus sign.
Hit it with a minus sign, right? We don't get fancy in this place. Oh! What the heck happened here? I hit it with a minus sign, but I hit it before I hit it with a minus sign. I hit it with a logarithm. Why? Same reason here. Does that violate the rule to hit that with a logarithm, or I still get the right global minimum? Abdullah?
Yeah, no.
What?
Doesn't
What'd you
violate.
say?
Doesn't violate the rule.
So it's okay to hit it with a logarithm first, and then hit it with a negative. Why is that combination of things? Why do we want to get? Now we're getting complicated. We're starting to act like mathematicians. Well, it turns out when you hit it with a logarithm, the derivatives, when you calculate the derivatives of the so-called probability function, are going to be easier to compute. Okay? Just a mathematical convenience. We hit it with a logarithm and a negative. But is this can this be thought of as a misfit function? Abdullah, say yes or no.
Yes.
No, it can't. What are you misfitting? You're not misfitting anything. Misfit means the difference between two things, right?
Right.
So what could this be called instead of a misfit function? She. Lee.
I think you need to.
What's a proper
Name.
The mathematician wants to keep calling it probability. I don't want to hear probability if I can help it.
Loss.
Objective function. Yeah. Why not use that as objective function? Because why? Because the right W is the one that's going to achieve what we want. Right? And at the bottom of that air bowl, better not call it air bowl, objective bowl, the derivative is going to be 0. So then we can use this stupid descent algorithm. Let's take a derivative of this guy. With respect to what? Abdullah.
W.
W1, W2, W.
Yeah.
Okay, that's the reason why I did that. And Abdullah's going to come in tomorrow and show what the derivative of this guy is. With respect to W1, W2, W. But I'm just going to plot something. I'm going to plot the observed minus the predicted. In this case, it's the observed for, red motorcycles. If I were to put, and I actually plotted this in MATLAB to convince myself this is true, it does something like this, right? It's a hyperbola that has a minimum over here and then comes back up. Okay? So I took the observed, and I then put in different values of z here to see how my misfit, I can call this a misfit function, behaves. Then I took this guy and plotted the same z's, and I can't call this a misfit function, this is a misfit function now. This guy looked like that. And this goes back to our observation a while back earlier that which would you prefer, and Abdullah convinced us that we prefer the ones that really are steep versus the ones that are flat. And it turns out the cross entropy for this particular example has a much, yeah, cheap.
You say the residual after using log L1 will make the function become steepest. But in this figure, you can multiple, for example, 100 with the normal 2 function.